Okay, here's the second part to 1.3, even, odd functions, symmetry. We're going to look at piecewise functions, talk about how to graph those in Desmos so that you don't have to do that by hand. And you'll love that about pre-cal. We start using the graphing calculator a whole lot more than we did in Algebra 2 Trig. Algebra 2 Trig, you had to do everything by hand. Fun times. And also the difference quotient. The first thing we're going to talk about is even and odd functions and what they look like graphically as well as algebraically. What makes a function even is if you take and plug in negative x everywhere you see a variable in your function, and the result is your exact same function that you begin with. So a function f is even if this is true. And this simply means if I take negative x and I plug into my function's equation and I get out the same exact function, it's even. Now, what this looks like graphically, your graph is symmetric with the y-axis. So it will have vertical symmetry. And so some examples, a very common graph that you're familiar with is a parabola. And I'll show you why that's the case algebraically. So y equals, I'm getting ahead of myself, y equals x squared, of course, is your parent function for your parabola. If we take and plug in negative x for x and square it, of course, you know, anytime you square a negative, you arrive at a positive. So we get back the original function that we started with. Another common graph that is also an even function, of course, is your absolute value or your cubic graph. So here, excuse me, not your cubic graph. But we could, of course, have a flipped parabola and so forth. So anything that would be y equals negative absolute value of x. So those are some examples and types of even functions. Even functions, once again, symmetric with the y-axis. A function is odd if you take and plug in negative x in the function's equation everywhere you see a variable, and you get out the complete opposite of your original function, which means that every term in the equation changes sign. Every term changes sign. The graph, what an odd function looks like graphically, it is going to have origin symmetry. So an odd function is symmetric with the origin. What this means, for example, one of the very common graphs that is odd and has origin symmetry is the cubic graph. And so it resembles this. Notice that if I have an ordered pair, a point on this cubic, if I plug in 1, then I'm going to get 1. So here's a point on the graph that I definitely know. And any ordered pair, such as 1, 1, is symmetric with the origin if the opposite of x and the opposite of y is also on the graph. Meaning the opposite of 1, -1, the opposite of 1, also -1. That point is also on this graph. So whenever that's true, that always indicates origin symmetry and that it's an odd function. The signs will be different. Or you can think about it also like this. They will be in quadrants across from each other, like diagonal quadrants. Another type of graph that would have origin symmetry is one resembling this, which is actually an actual transformation of this graph. So another type. And you're going to see what that looks like algebraically later on. Even, symmetric with y. Odd, symmetric with origin. Okay, checking this algebraically. You want to plug in -x for every single variable. Here's how you determine if it's even. If you get the exact same function you begin with when you plug in -x and simplify, it is an even function. So meaning that everything in that entire equation stays the same. Same sign, same exponent, everything. If you plug in -x and you get that all signs change, then it's odd. All the signs have to change. So it either all has to stay the same or all the signs have to change. If it doesn't stay the exact same or all of it does not change, then it would be neither. So if you get the exact same equation, even, all the signs change, it's odd, and if some of it changes, it's neither. Okay, in the next 4 problems, we're going to practice determining algebraically whether each function is even, odd, or neither. In part A, we have function f of x equals x squared minus x. If we take and plug in -x everywhere we see an x, and simplify, of course, -x squared, that's going to stay positive, and then this would actually become positive x. So then you compare this to your original. And of course, it did not, all of it did not stay the same. The x squared did stay the same. However, the -x changed to a positive x. So all of it didn't change, all of it didn't stay the same. This is neither. You'll see in a minute, hopefully, a shortcut to help you figure this out. In part B, and maybe some of you already know, let's plug in -x everywhere we see an x. anytime you raise a negative to an odd power, it always stays negative. So this stays negative, or this becomes, rather, sorry, negative x to the third. And this, you bring down this minus sign, negative x to the fifth, you have to do exponents first. Think about distributing that minus sign. So before I can make that a positive, do your exponents. So that actually stays negative x to the fifth, and eventually, and it becomes this. So compare that to your original. The x cubed did change to a negative, and this minus x to the fifth became a positive. So when we compare, it all changed, so it's an odd function. You can actually check these in Desmos just to see it graphically if you wanted to. This graph, you would see that it has origin symmetry. So it would be in, its parts would be in diagonal quadrants. This would definitely not be symmetric with the origin or the y-axis. All right, part C. We're going to plug in negative x once again, same thing. So negative x squared, 1 minus negative x squared. You have to be really careful on this one. This one gets people every year. You actually consider this to be one term because it's all multiplied together, even though you have minus underneath the radical, but this is still only one term. So if this outer part stays the same, it's actually even. If this outer part changed, it would actually be odd. This stays the same. It actually does stay the same underneath, but let's say that this changed, but that part stayed the same. It would still be even. So a shortcut for you to do this in your head without having to do much work and easily determine even, odd, neither, look at your exponents. You know that if you raise an even exponent, raise a negative number to an even exponent, it becomes positive. If you raise a negative to an odd exponent, it becomes negative. So notice in this case, both of these had odd exponents. Both of them changed signs. Odd. Notice you only had one even exponent. This is an odd exponent. This one stayed the same. That one changed. Neither. In this case, the exponent I'm mainly concerned about is outside the radical. It was even, so it didn't change. Even. And think about this here. If I raise a negative x to the 6th power, negative x to the 8th power, they're both going to stay the same. So this one will be even. So in other words, if you have all even exponents, then it's going to be even. If you have all odd exponents, it will be odd. If you have a mixture, neither. Number 2, let's see what this looks like graphically. Use symmetry to determine if each graph is even, odd, or neither. In part A, that is definitely symmetric with the y-axis, and the type of function that is symmetric with the y-axis is your even functions. So even y. B is definitely symmetric with the origin. Once again, you can check. Let's say that point 1, is on the graph, then we would know that point -1, -1 is on the graph. It is the exact graph in opposite quadrants. So odd. And part C, you can definitely tell this is neither right off the bat. This graph definitely doesn't have any type of symmetry along the y-axis, origin, so on. Okay, what we're going to look at next is the type of problem that ties in everything that we've already talked about so far in 1.1.1.2 and 1.3, domain, range, X-intercepts are zeros, increasing, decreasing intervals, so many fun things. In this particular graph, notice we have parts A through L, and we're going to go through and discuss each one of them. In part A, let's talk about the domain of this graph. Recall, domain is how far left your graph goes, how far right your graph goes, and range is how far down it goes, how far up. So domain, let's examine this graph. In relation to the x-axis, it goes left forever. So remember, always write your domain and range in order from least to greatest. And we read the graph left to right coming back. There's no gaps in the middle. And in relation to the x-axis, it ends at 6. Notice that is a closed-in dot. It does not keep going. So 6, and that should get a bracket, and there's your domain. Remember, domain and range does use parentheses and brackets. Recall that increasing, decreasing, constant are the ones that only use parentheses. Part B, range. Examining how far down our graph goes in relation to the y-axis. So notice that this part keeps going down forever. Even though this part ends, it's going to go down forever. So we say negative infinity. And the graph comes up and maxes out at 1. And it does touch 1, so we're going to put a bracket. Part C, the zeros of a function are simply another name for x-intercepts. So where does the graph cross the x-axis? You can see that the graph is crossing at -3 and +3. Write them as an ordered pair. So -3, 0, and at 3, 0 is where it's crossing the x-axis. Remember, always with an x-intercept, your y's are 0. So -3, 0, and 3, 0. Part D, it asks you to find f of 0. So what you're looking for, they give you x is 0, you're looking for the y. So go to the x-axis. You're trying to find what ordered pair is on this graph that has an x value of 0. So 0, here's the graph, and go up to that graph, and it would be 1. And I told you when we were doing this in the last lesson, you can always double check, make sure ordered pair 0, 1 is on your graph. The next 3 parts, increasing, decreasing, constant intervals. Remember that increasing is, of course, going uphill, and I told you that you can draw a figure on top of your graph walking left or right if they're walking uphill, increasing. So notice that if I'm reading my graph left to right, then if I had a person here, they would be walking uphill, and since this graph goes on forever left, negative infinity, and we only use x values. Remember that through here. So negative infinity, and it comes back, stops increasing at -2 there. And we always just use parentheses. Then it is constant from here to here. And the x values for that interval are -2 to +2. And finally, this graph has a decreasing part. Notice that it does stop at 6. So we're going to say it decreases from 2 to 6. From 2 in relation to the x-axis to 6. H. We want to find the values of x for which y or f of x is greater than 0. So this makes you think a little bit. So this is saying what part of your graph is y greater than 0? Well, we definitely know that above the x-axis, my y values are greater than 0. But what are your ranges of x values for that graph? So once again, and I'm going to highlight that for you to show you. So here's the part of the graph that has all y values greater than 0. Does that make sense? Like my y here would be decimal, decimal, decimal. My y is 1, decimal, decimal. But when we get to any point on this part or any point on that part, my y would be less than 0. So let's look at the range of x's, because that's what it's asking for. All the values of x, where y is that? So notice that when my x is negative 3, on all the way to positive 3, all those ordered pairs, or that part of the graph, would have y's that fall within that range. Therefore, you would say from negative 3, bracket, include it, all the way to positive 3, bracket. All of those x values would have that. It's a little bit different. It's a little bit different way of thinking about it. On that part I, the values of x for which f of x is equal to negative 2. So in this case, they're just wanting you to look at one y value. So lucky you in this case. So find where y is negative 2. So we're going to go to the x-axis at negative 2. But I want you to notice something. So here we're at negative 2. But you actually have two parts of your graph, here and here, that would have a y value of 2. So the two x values, you've got 5 and negative 5 are your two x values that have y of negative 2. Okay, we're almost finished with this problem. Hang in there. Is f of 4 positive or negative? So f of 4, they give you y of 4. So let's go to the y-axis of 4. Go where your graph is here. Well, that definitely is going to have a negative y value. And that's what they're asking for. They're saying find f of 4. They give you x. They want you to find y. So this is negative. Once again, we went to the x-axis at 4. And then went to the graph. The corresponding y is negative. Part K, is this function even, odd, or neither? So you can definitely see that it doesn't have exact y-axis symmetry because this part ends. Now, if this part kept going infinitely, it would be even, but it does not. And it's definitely not odd either. Last part, is f of 2 a relative maximum? So let's find where f of 2 is at. Go to your x-axis at 2, since they give you 2. Go to your graph. And this point be careful here. This is actually not a relative maximum. And remember, a relative maximum is where a graph changes direction from increasing to decreasing. This point changes direction from constant to decreasing. So it's close, but it's not a relative maximum. Remember, relative maximum is where you're topping out roller coaster hill and getting that maximum thrill. Okay, last but not least, piecewise functions, everyone's favorite. I heard there was a pretty nasty problem in Delta Math that I'm going to examine for you. You'll be happy to know also, I'm not going to make you graph these by hand. We're going to type these into Desmos, and I've posted a link to your Schoology to show you how to do that. It's actually very simple. Okay, piecewise functions, they are functions defined by two or more equations over a specified domain. If you have ever, well, you probably don't pay your own bills, or probably don't pay certain bills anyway at your house, but let's say that your telephone bill or cell phone bill. Some plans, of course, have data overages. Your bill is a certain amount up until you use a certain amount of data. Then once you go over that data, you have to pay like $15 per gig or a certain amount. So you can actually model a simple piecewise function for that particular issue. But also, of course, businesses and places can use piecewise functions to model profit after a certain margin. What a piecewise function looks like, and if you recall, early Algebra 2 trig last year, we graphed absolute value, and Ms. Rogers, Ms. Shields, and I made you write them into a piecewise before you graphed them, and it was fun. You guys loved it so much. Not really. This is your equations that are your pieces of your graph, and this is actually your restriction. So, for example, this would be an upside down parabola, but you would only see the left part of the parabola up to +1. So the right side of it would be cut off. This graph would actually be a line, but once again, you would only see the left part of it because anything to the right of +1 in relation to the x-axis would be cut off. And you can type those in and see them. So yay, not graphing by hand. We will evaluate, that's what I'm going to show you, and plug in and then graph them electronically. Evaluating piecewise function, how you do that is you simply look at the value that they give you and you look at your domain restrictions, which are at the end. Figure out, well, does the number they give me, does it fall within x being, is it greater than 5, less than 5, equal to 5? So you have to determine which case it falls into. When you do that, you are going to use the corresponding equation to plug into. So number 4, they give you this beautiful piecewise function. For the top piece, you have this restriction. And for the bottom piece, you have this restriction, x less than or equal to 5. In part A, they ask you to find g of 0. So what you do, going back to your steps, you're given value 0. Which domain does that fall into? 0 is definitely less than or equal to 5. So 0 falls within that restriction. So we're going to use this bottom equation to evaluate g of 0. So I take this and I simply plug in 0 and I get -5. And that's your answer. Part B, our given value is -6. It falls into this restriction also. -6 is less than or equal to 5. So we use this equation to plug -6 into. So square that. Be careful here. Negative 6 squared is actually going to give you 36. Bring down that negative sign. Negative 41 is your result. Number 5. Last but not least, we are given this piecewise x squared minus 25 over x minus 5 if x is not equal to 5. So in this case, the only time, we use this equation every time we get a value other than 5. But you're going to love this one. If they give you 5 or ask you to find h of 5, your answer is 10. So they're telling you, hey, your answer, your function value is 10 when x is 5. So there's no work to that one. So hint, hint, I've already told you the answer to B. Part A, h of 7. So all we have to do, of course, is figure out which one of these that 7 falls into. Well, 7 is not equal to 5, so it falls into that category. So we use this equation. So we're going to plug in 7, and I'm going to show you a shortcut for that. Do you guys remember that the x squared minus 25 is a difference of 2 squares, and that will actually factor, because if I'm you, if I can see that, I'm going to simplify this first before I plug 7 in and square it and then have to deal with those nasty fractions. So remember that the difference of 2 squares factors into x plus 5, x minus 5. And then look what happens. Those x minus 5s cancel off beautifully. So all you're left with is x plus 5. And now all I have to do is actually take 7 and just plug in here. So 7 plus 5, 12. But of course you can just plug in 7 squared, 7 minus 5 on the bottom, and you will get the same thing. Okay, part B, h of 5. Well, they actually tell us that x is 5, so guess what? My answer's 10, no work. That's it. Don't you love those? Do you want me to give you all of those on the test? Alright guys, that concludes 1.3 part 2. I hope you've had a great day. There's only one small part of 1.3, and I'm going to do a video on it by itself and upload that. It'll be a very quick video on difference quotient that you've never seen before, that you will use in calculus if you plan to go that route. Thank you guys. Have a good day.